Alright, ladies and gentlemen, this is our free fall review video. I'm just going to briefly go over the main concepts regarding free fall problems in the one dimension, because this is especially going to be important going into the 2D kinematics unit. And we start here with acceleration due to gravity. So this means now that we're working vertically, gravity is going to be a factor in here. So that means our acceleration, we call it acceleration due to gravity, comes with a specific constant number, and that's 9.81 meters per second squared on Earth, and this is also on the reference table, so you don't have to memorize this. It's going to come useful, especially since we use it so often. You're going to start to remember it anyway, and this number is constant. It doesn't change. It's always going to be 9.81 on Earth. That means your acceleration is a constant rate, which causes our speed to change at a constant rate. Now, second point, we neglect friction and air resistance in our problems. So that simplifies our problems a lot more, which means mass doesn't matter. We're dealing with how we describe motion vertically. We don't care about how and why and how mass is going to affect that because we're neglecting friction and air resistance. Lastly, we care about direction. Direction matters. So we have to check whether or not the object is moving up against gravity or going down with gravity. So if it's going down, your objects are going to speed up because it's following gravity. Gravity's pulling it downward, so it's going to accelerate. So this is with gravity. And then the second bullet point here, objects slow down going up. This is against gravity. Hence, you make your acceleration negative. So this leads to positive 9.81 when you're dealing with problems, and this one leads to a negative 9.81. This will ease our calculations, making it positive and negative. And you'll see why, and if you look at your numbers, they'll start to make sense. If you have, let's say, an object slowing down, so you should see your speed decrease in number. You shouldn't end up having a higher number because you accidentally made it a positive acceleration when you're supposed to slow down. So that's an example right there. Alright, now I still also want to talk about acceleration. I saw this mistake done on the IA where we think that acceleration is changing, but here our accelerations are moving at a constant rate. This is a constant number. We don't see that number change, hence why we call it a constant. But because we have an acceleration, speed is changing. Our velocity changes. So velocity can go up or velocity can go down. So this is changing. Alright, oops, that was a mistake there. Alright, so if we think about it in terms of graphs, you want to show that your speed is changing at a constant rate. And if we're looking at position versus time, distance versus time, it's going to be an exponential change in distance, like that, to show that we are accelerating. Now we're going to talk about our first scenario, object drop. So when you're holding an object, so pretend you're holding an object and you're just about to let it drop. Before you let it go, your initial velocity will always be 0. It's at rest right before you drop it. Now because objects being dropped are going downward, your acceleration is a positive 9.81. This is our convention in the class. Distance, they'll give you, time they'll give you, and then final velocity they might give you too, but all of these other three variables are fair game when it comes to solving. They're either given or you have to solve for them. Now the difference here in our second scenario is that when you're throwing an object downward, your initial velocity will not be 0. So that means you're given a velocity value. Acceleration is still positive 9.81, and the rest of the variables again are fair game. And our last scenario is probably the trickiest one. Will especially be important for next unit when you throw an object up. So it follows a parabolic path where you could divide this up into two halves. This is symmetrical motion. So that means if, let's say, you give it an initial velocity right here of 5 meters per second, going upward, this peak right here will always be 0. And then it goes back down, where here the velocity upon return is equal to your initial velocity, which is 5 meters per second in this example. So it goes up, it leaves your hand at 5 meters per second, and it comes right back down to your hand at 5 meters per second. It's symmetrical, equal, but opposite in direction. And it's the same if we talk about time. If you throw an object up, and let's say it takes about 4 seconds to go up, then it will also equal 4 seconds to go back down. So that means your total flight time is 8 seconds, equal but opposite. You could split this entirely in half. Now when it comes to values, your initial velocity again won't be 0 because you're throwing something up. Your acceleration going upwards now is a negative 9.81 meters per second squared because we're going against gravity, so we're slowing down. But if you're going to take it from the peak going back down, so your acceleration going back down, that's when you turn it into a positive 9.81 meters per second squared. T is fair game, D is fair game. That's usually distance to the peak. And your final velocity, which is usually the peak, when you're going upward, is 0 meters per second. Now, if you're going from the peak back to where you started, you kind of have to flip it around, where your initial velocity is 0 because you're starting at the peak, and then your final velocity going back down will be exactly what you started out with. All right. And here, that is the end of this brief free fall review. You might want to check back here for a 1D relative velocity, as well as go back to reviewing free fall again when we get to 2D kinematics.